Hey there, science fans. Today we're diving into the fascinating world of solutions. We're going to explore how and why things dissolve, how ions move around, and what that means for electricity. Get ready because we're about to unlock some serious chemistry knowledge. Solutions are everywhere, from the oceans to our own bodies. They're mixtures where one substance dissolves evenly into another. We call the dissolving substance the solute, and the substance it dissolves into the solvent. Understanding how these solutions behave is key to understanding many chemical reactions and natural phenomena. Think about salt dissolving in water. The salt crystals seem to disappear, but they're still there. They've just broken down into individual ions, charged atoms, that are now surrounded by water molecules. This process, my friends, is called solvation, and it's the first stop on our chemistry adventure. So, buckle up and get ready to explore the amazing world of solvation, hydrated radii, ionic mobility, and electric conductance. It's going to be an electrifying ride. Let's dive deeper into solvation. Remember how salt dissolves in water? That's because water molecules are attracted to the charged sodium, Na+, and chloride, Sil, ions in salt. These attractions are what we call intermolecular forces. Water is a polar molecule, meaning it has a slightly positive end and a slightly negative end. This polarity allows it to interact with and surround ions, effectively dissolving them. The positive end of a water molecule is attracted to negative ions, and the negative end is attracted to positive ions. This process of surrounding solute particles with solvent molecules is what we call solvation. The strength of these solute-solvent interactions determines how well a substance will dissolve. If the interactions are strong, the substance will dissolve easily. If they're weak, it might not dissolve much at all. Solvation is essential for many chemical reactions. It allows reactants to come into contact with each other, which is necessary for them to react. It also helps to stabilize charged particles, preventing them from recombining. So next time you stir sugar into your coffee, remember the amazing process of solvation at work. Let's talk about hydrated radii. Ions form a sphere of water molecules around them. This sphere is called the hydration shell. The size of this shell determines the ion's hydrated radius. It affects how easily the ion can move through a solution. Let's talk about how ions move in a solution. This movement is called ionic mobility. Imagine a racetrack with ions as the racers. Some ions are faster, some are slower. The size of the hydrated radius is one important factor. Smaller hydrated radii mean less drag, allowing the ion to move faster. Larger hydrated radii create more drag, slowing the ion down. So the next time you see a sports drink with electrolytes, remember those charged particles are racing around. Section 5. Electric conductance, the flow of charge. Now let's electrify things. Electric conductance is the ability of a solution to conduct electricity. This ability depends on the presence and mobility of charged particles, like our speedy ions. Imagine a wire with electrons flowing through it. In a solution, the ions take on the role of the electrons, carrying the electric charge. The more ions present in a solution and the faster they move, the better the solution conducts electricity. We measure electric conductance in units called Siemens per centimeter or S per centimeter. A higher value means a better conductor. Pure water, for example, has very low conductance because it contains very few ions. But add some salt and watch the conductance shoot up. That's because the dissolved salt provides a plethora of mobile ions to carry the charge. Electric conductance is crucial in many applications, from batteries and electroplating to measuring water purity, and even in our own bodies, where electrolytes play a vital role in nerve impulse transmission. So remember, whenever you see electricity flowing, there's a good chance ions are involved in the action. Section 6. Connecting the dots. From solvation to conductance. We've covered a lot of ground, so let's connect the dots. We started with solvation, the process of surrounding solute particles with solvent molecules. This process is influenced by the interactions between the solute and solvent, like the attraction between water molecules and ions in a salt solution. We then explored hydrated radii, the size of an ion, plus its surrounding water molecules. Smaller ions tend to have larger hydrated radii due to their higher charge density. The size of the hydrated radius affects an ion's mobility, or how easily it moves through a solution. Ionic mobility, in turn, directly influences electric conductance. The more mobile the ions are, the better the solution conducts electricity. Factors like temperature, viscosity, and the strength of the solute-solvent interactions all play a role in determining ionic mobility and, consequently, conductance. So you see, these concepts are all interconnected. Understanding one helps us understand the others, and provides a deeper insight into the fascinating world of solutions and their properties. Section 7. Real-world applications, from batteries to our bodies. The concepts we've discussed are not just confined to textbooks. They have real-world applications that impact our daily lives. Let's explore a few examples. Battery technology. Batteries rely on the movement of ions in an electrolyte solution to conduct electricity and store energy. Understanding ionic mobility and conductance is crucial for designing more efficient and longer-lasting batteries. Electroplating. This process uses electric current to deposit a thin layer of metal onto a surface. The rate of deposition depends on the ionic mobility of the metal ions in the solution. Water purification, conductivity measurements help determine the purity of water. Higher conductance indicates a higher concentration of dissolved salts and minerals, which may require further treatment. Physiology. Electrolytes in our bodies like sodium, potassium and calcium are essential for nerve impulse transmission, muscle function and maintaining fluid balance. Their movement and conductivity are crucial for our overall health. These are just a few examples of how understanding these fundamental concepts can lead to advancements in various fields and impact our lives in countless ways. Section 8. Wrapping it up. Key takeaways. We've covered a lot of ground today. Let's recap the key takeaways from our exploration of solvation, hydrated radii, ionic mobility and electric conductance. Solvation is the process of surrounding solute particles with solvent molecules driven by intermolecular forces. Hydrated radii refer to the size of an ion plus its surrounding water molecules, which influences its mobility in solution. Ionic mobility is the movement of ions in a solution, affected by factors like hydrated radius, viscosity and temperature. Electric conductance is the ability of a solution to conduct electricity, depending on the concentration and mobility of ions. These concepts are interconnected and have wide-ranging applications in fields like battery technology, electroplating, water purification, and our own physiology. Section 9. Keep exploring. Chemistry is everywhere. As we've seen, chemistry is not just about beakers and labs, it's all around us, explaining the world we live in. From the simple act of dissolving sugar in our coffee to the complex workings of our bodies, chemistry is at play. So keep asking questions, stay curious, and never stop exploring the wonders of science. There's always more to learn and discover, and who knows, maybe you'll be the one to make the next groundbreaking scientific discovery. Keep those brain cells buzzing.